Here we are in chapter 20. We're going to get all reactive here. We're talking about chemicals and how they react and chemical reactions. So let's start with, we've been talking about physical versus chemical changes. But usually in science, once we talk about physical and chemical changes, when we talk about chemical changes, we don't call them that except for when we're comparing them to physical changes. Okay, physical changes don't change the chemicals that are present. Chemical changes do. Okay, now, um, when we actually have these chemical reactions, which, all right, we tend to call them chemical reactions, not chemical changes. All right, chemical changes we do when we're talking about physical versus chemical, but most of the time, a chemist would just say, we're talking about this reaction, okay? So we're talking about the chemical reactions, and that's what we're kind of looking at here. Now, we've talked about formulas. We use a formula to show which ones we're putting together to get these reactions, all right? And so in this case, we're taking hydrogen gas and we're adding it to oxygen gas, and we're going to get water. Okay. Now, a couple of things that we do is, first of all, the chemicals that we start with are called our reactants. In this case, we have two reactants. We have hydrogen and we have oxygen gas. Now, um, they're reactants because they're going to react with each other, and they're always going to be on the left side of the arrow. The arrow basically here means this is where the reaction happens. Anything to the left of the arrow over here is going to be the reactant, what we had before the reaction happened. In this case, we have two. You could have one reactant breaking down into several products, okay? But whatever we end up with on the other side is called our products. In this case, actually, it would be a product because we're only getting one, and that's water. Sometimes it's one, sometimes it may also be several things. So it can be product or products, either way. All right. So basically, you just remember the reactants react to produce the products. All right. And that's going to be true of any chemical reaction. Whatever's on the left side is the reactants, whatever's on the right side are the products. Now, just to complicate things a little bit, there are some reactions which you will see a double arrow, which means they kind of go back and forth depending on the temperature and depending on other things that are happening in the environment. This actually can go back and forth. But for most parts, we talk about a reactant and it goes toward the products. Now, depending on the equation, sometimes it will give us a little more information. For example, we will sometimes see the little g in parentheses after a symbol. And in this case, both hydrogen and oxygen would have that. And that tells us that these are gases. Okay, so a little g in parentheses would tell us that it is a gas. All right. Water, on the other hand, is a liquid. So we would put in parentheses with the L there, a little L, that looks kind of like a 1, but actually that's a little L, and that would show that it is a liquid. All right. Now, other things that you might see then, not surprisingly, is S. Okay. And you can probably guess that if L is liquid and G is gas, then S is probably going to be a solid. Okay. For example, if we had NaCl, which is table salt, we would put a parentheses S after it. However, if you use table salt as a solid, it doesn't react very well. It needs to be dissolved in something, which is water, and for that we use this symbol, which means aqueous, which means it's dissolved in water, okay, or some other liquid, depending on uh, the reaction, but usually water is our most common solvent. Sometimes we call it the universal solvent because that's usually what we're talking about. All right, and that just means the salt has been dissolved in water, so now it will react better. All right, that's not the same as L because L would mean that solid, if you actually heated up salt enough that it melted, which can be done, but it has to be done at very, very high temperatures, then you would put an L, but very rarely is that going to be the case. Most of the time you will see the AQ a lot of times because many chemicals are dissolved in water to help make them react. The little letters underneath are called subscripts, okay, and because they are below the line. Okay, subscripts, we have 3 of those here. That tells us how many atoms we have in each molecule here. We have one molecule of hydrogen, one molecule of oxygen with two atoms and two atoms, and then we have water over here with two hydrogens and one oxygen. We cannot change the number of subscripts without changing the element. For example, if we change this to H3O, there is such a thing, but it's not water anymore. Okay, it's H3O. It would be different. Okay, that's something different. Alright, so you cannot change the subscripts without changing what it is. Okay, however, if we need more, so for example, over here we have two hydrogens, over here we have two hydrogens, over here we have two hydrogen oxygens, but we only have one over here. Where'd that other one come from? Well, the way the reaction is written is not balanced and it cannot work. Therefore, we would need to put a coefficient. Okay, this big 2 in front of it is a coefficient. It does not change what the molecule is. It just says that we have to have two of them. So now we have two molecules, and if we were thinking in math terms, it would be 2 times everything in parentheses. So now we have one oxygen here, but we have times the 2 here tells us we have 2 oxygens and we have 2 oxygens. Unfortunately, now we have 4 hydrogens, so we have to go back over here and put a 2 here. So we have a total of 4 hydrogens, and over here we have 4 hydrogens. We have 2 oxygens and 2 oxygens. So for hydrogen, oxygen, and combine and make water, which they do, you would have to have twice as many molecules of hydrogen as oxygen in order to make it come out even. And that's what the coefficients do. They allow us to change the number of atoms involved so that it'll come out even without changing what the molecules are. All right, and it's kind of like a ratio. You need a 2-to-1 ratio of hydrogen to oxygen to get 2 molecules of water. All right. Now, why do we have to have it balanced? Well, because of anytime there's a chemical reaction, we cannot have stuff that just matter that just disappears. Okay, matter can't just go away. It's still there, and so you have to have the same amount of matter before as you do after, and so that's why you have to balance it out so that you have the same amount on each sides. Okay, because you can't do an experiment. If we burn a piece of paper, the mass of the piece of paper before and the mass of what's left after has to be the same. But someone says, well, the ashes aren't going to weigh as much as the paper did. That's true. But if you captured the water vapor and carbon dioxide and other gases that are given off as smoke and soot, it would still weigh the same. The mass before and the mass after have to be the same. And this is the law of conservation of mass. Or you may just hear someone talk about the conservation of mass. All right. In other words, matter cannot be created or destroyed. All right. The amount of matter before the reaction, the amount of mass or matter afterwards, can't be different. You have to have the same amount afterwards that you began with. Now, the exception to that is if you have nuclear fission, which is where you take a uranium atom we talked about and split it into smaller pieces. Some of the matter is actually, or mass or matter, is changed into energy directly. Okay, and in fusion, where you're taking fusion is where you're taking hydrogen atoms and fusing them together to make helium atoms. Once again, some of the matter is literally changed into energy. So there's another law which kind of supersedes this one, which is the law of conservation of mass and energy, and says the total amount of mass and energy cannot be changed. But short of nuclear reactions, which are very rare in nature and rarely occur, that we see, for most chemical reactions that we're going to talk about in the lab, law of conservation of mass works quite fine. And basically, we can't create or destroy. We have to end up with the same amount. And that's why we have to balance the equation. Okay? And as we said earlier, you can't change the subscripts because that changes what the molecule is or what the chemical is. But you can change the coefficients which we put in front of it. Okay, so another example, if we took sodium, which is a metal, very reactive, and add it to water, okay, it will react and it will create sodium hydroxide plus hydrogen gas. All right, and so to do this one, we would have to balance it and have to have the same amount on both sides. And if we do this, we just need to take count of how many sodiums we have. We have one over here, and we have one over here. All right, and so far so good. All right, now we have two hydrogens here, and over here we have three hydrogens. That's not going to work. Now, very simply, since this number is H2O, no matter what number we put in here, it's always going to be even. Usually the first thing you want to do is take the odd one and do something to make it even. So I would put a 2 in front of this, and now there's two hydrogens. Two hydrogens makes a total of 4. Okay, so now I have a total of 4 hydrogens over here, but I only have 2 over here. So I'm going to have to put a 2 in front of it, and now I have 4 hydrogens. All right, but over here now I have, instead of 1 sodium, I have 2 sodium. So I go back over here, I'm going to have to put a 2 in front of that because now I'm going to have 2 sodiums. So that balances. Now let's look at our oxygens. Oxygens, we have 1 here times the 2 here, so that gives us a total of 2. All right, and here we have 1 times the number in front, because remember this number is like putting parentheses around the whole molecule. And so 2 times that, so I have 2 oxygens there. And now everything is balanced. So if I put 2 sodium atoms plus 2 water molecules, and that will give me 2 sodium hydroxide molecules plus hydrogen gas being given off by itself. All right. And if I wanted to do a little farther, I could put the symbols. This is a solid. Water is a liquid, so I'll put a little L. Sodium hydroxide is going to be dissolved in water. I would have a water solution left, so it'd be aqueous. And hydrogen gas is going to be a G because it's a gas. All right, and that would be our completed balanced formula. Now we're going to talk about reaction rate. How fast do compounds and elements react when they come together? Well, first of all, in order for them to react, a couple things have to happen. One, they must collide with each other and must be near enough to each other to react. So they've got to hit each other. Okay, and then once they hit each other, they can react and do that. Okay, but they also have to come and hit from a certain direction, a certain orientation, and line up. And they have to hit with enough force to cause them to react. If they come very slowly, they may not have enough energy or whatever to actually react with each other and change. And so the atoms may not combine with each other. They may just bounce off of each other. And so they must collide with each other, and they must be near each other in order to react. Okay. Now, one of the reasons we dissolve things in water is because that allows them to move around and move more freely and hit each other and bounce around and orient themselves differently and stuff, and that allows them. Now, when we look at their concentration, uh, let's just look at any reaction and look at how fast it's going to happen. When you look at a reaction, you have your reactants, in this case the yellow dots, and represent two chemicals put together, could be oxygen, for example, and blue dots, which could be hydrogen. They may be different colors, but I'm colorblind, so cut me a little slack there. All right, but basically, at first, when they first start mixed together, you have lots of them, and so it's very easy for them to run into each other, and so they start reacting very quickly. And so they start reacting, you start seeing products, one of each atom put together now to make new molecules. But as you get more and more the reaction goes, there's fewer and fewer of them that haven't reacted. So obviously it's going to be harder for them to run into each other or to meet each other, since they're surrounded by these other molecules that have already reacted. So the reaction tends to slow down, and it eventually will stop when all the molecules have combined, or all the available molecules have combined. For example, we might still have blue ones, not quite the same shade, but there you go. But if there are no more yellow ones to react with, then the reaction will stop, okay? And we would say in that case the yellow was the limiting reactant because it limits the reaction, because you ran out of it, there's not enough of it left, and so it stops it. And we would say that the product of the reactant that was in excess would be the blue, because we had more than enough of it. But once you run out of the limiting one, then it stops. Okay, so the limiting reactant is gone, and the reaction slows down. In our next video, we will look at the couple things that affect it: the concentration of the chemicals put together in the water or whatever we're mixing them together with, and the temperature, and then we'll look at the effect of enzymes. But we will get into that in the next video. Thank you for watching, and we'll see you then.